I am R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we will discuss the topic on capacitance of coaxial cable and also energy and energy density in a capacitor. So, first we see how to calculate the capacitance of a coaxial cable. We know coaxial cable consists of two conductors sharing the same axis. So in the diagram we have a coaxial capacitor and let A be the inner radius and B is the outer radius. The two concentric conductors are separated by a dielectric called permittivity epsilon, and the length of cable is taken as L meters. Here we are assuming the inner conductor carries a charge density ρ1 coulombs per meter and is on the surface and equal and opposite charge density of minus ρl coulomb per meter exists on the outer conductor. So now if we calculate the charge Q is given by multiplying the charge density and its length. So Q can be expressed as ρl into L. Now we are assuming the cylindrical coordinate system because the coaxial cable configuration fit into the coordinate system of cylindrical, and here the electric field is radial from the inner conductor to outer conductor, and for finite line charge it is given by electric field vector E is equal to ρl by 2 pi epsilon r into AR vector. And now the electric field is directed from the inner conductor to the outer conductor. The potential difference is work done by moving a unit charge against the electric field from R is equal to B, that is from outer conductor radius, to R is equal to A, the inner conductor radius. So the potential difference can be written in the direction of radial and is given by V is equal to minus integration of E dot dl, or it is equal to minus integral of the limit is R is equal to B to R is equal to A ρl by 2 pi epsilon r into AR, and this is equal to dr AR. And now the finalized formula for the capacitance is Q by V. So Q is ρl into L, V is obtained now after integration, that is ρl by 2 pi epsilon ln of B by A. So summarizing, we get the total capacitance of a coaxial capacitor C is equal to 2 pi epsilon into L divided by ln of B by A farads. And now to find out the energy and energy density of a capacitor, the energy is nothing but the energy stored in a capacitor is electric potential energy and is related to the charge density Q and the voltage V on the capacitor is, and the energy density of a capacitor is a measure of the amount of energy stored in a given volume of the capacitor, and it is an important parameter to consider when designing or selecting capacitors for various applications, as it can influence the size and efficiency of the devices. So now take the configuration of parallel plate capacitor, and it is applied with the voltage V, and here AN vector is the direction normal to the parallel plates. So the electric field E can be given as V by D AN vector, and the energy stored is given by WE is equal to 1 by 2 volume integral of D dot E dV. So it is equal to 1 by 2 volume integral of epsilon E dot E dV, and E dot E is modulus of E squared, and this can be given by 1 by 2 epsilon A by D V square. So the energy stored in a capacitor is given by W is E is equal to 1 by 2 the capacitance C potential difference V the square in joules. So energy density is WE is equal to 1 by 2 epsilon integral of volume integral modulus of E square dV. So the energy density can be given as WE is equal to 1 by 2 epsilon of modulus of E square joule per meter cube. And by substituting the displacement density vector D is equal to epsilon E, we can write the energy density WE is equal to 1 by 2 D squared by epsilon, or it is also equal to 1 by 2 D vector E vector joule per meter cube. And now the factors affecting the energy density of a capacitor is dielectric material. So the dielectric material greatly influences its capacitance, in turn its energy density, and the material with higher dielectric constant can store more energy per unit volume, resulting in higher energy densities. And its geometry and design also influence the geometry and design, including its shape, size and arrangement of the plates, and will impact on energy density. So a larger surface area of the plates and smaller separation between them generally result in higher capacitance and energy density. So the third parameter is the operating voltage. So this also have influence the capacitance and energy density value. So the voltage applied to the capacitor directly affects the amount of energy it can store, with higher voltages resulting in higher energy densities. However, capacitors have a maximum voltage rating beyond which the dielectric may break down and the capacitor may fail. So the applications of capacitor energy: the audio equipment, uninterruptible power supplies, camera flashes, pulse loads such as magnetic coils and lasers use the energy stored in a capacitor. So assessment questions: what is the capacitance of a coaxial cable? We obtain from the derivation. And energy density, an important parameter of a capacitor, and energy stored in a capacitor we have seen from the parallel plate capacitor. Thank you.